So I'm holding in my hand a spool of carbon nanotube fibers. So this is a continuous fiber. It's about as thick as a human hair, and it's about 50 meters long on this single spool. So this spool has trillions and trillions of carbon nanotubes that are all aligned in the same direction along the axis of a fiber, and they're very well packed. And because of this structure, we now can translate the amazing properties of carbon nanotubes, which are nanoscale properties. We can now translate it onto an engineering fiber, which is something that we can handle on the macroscopic engineering scale for applications.
So what you're looking at here is 2 bundles of our nanotube fiber that are holding up an LED light bulb that weighs 50 grams. Those fibers are also being used to run the current that's powering the bulb. So this is demonstrating the multifunctionality of the fibers, that they are strong enough to support the weight of the bulb and also have high enough conductivity to provide the current.
This is just some fiber that I took off the drum, which was not under controlled conditions, but it's still good fiber. We don't know exactly what the conditions were, so we don't keep it. But you can see that it has a lot of strength. This thing is actually pretty heavy. This is the spinning cylinder. So we have carbon nanotubes that are dissolved in a solvent, which is chlorosulfonic acid. And this solution is a very viscous type of material, so it's kind of like mayonnaise almost in viscosity. And we're extruding it through 19 small holes and then winding it onto a drum.
This is a spool of the fiber. After it's been spun and wound, this is one continuous filament. So this was produced in a single spinning experiment where we spun a continuous filament and then were able to wind it onto a spool like this. The machine we're sitting near here is the SEM, the scanning electron microscope, and we use this to do high magnification imaging of the surface of our fibers so we can get an idea of what the structure is on a microscopic scale, the scale of a couple of micrometers or a few nanometers, tens of nanometers.
The cool thing about it is you have a material that's very strong and highly conductive, so it has properties and high-strength materials like carbon fiber. But on the other hand, you can handle it like you essentially a textile, not like a rigid material.
The main improvement that in terms of our process versus other work that's already been done on fabricating nanotube fibers is that if you use a wet spinning process, as we've developed here, you have a very scalable process. So you can easily scale up to make more and more material without necessarily increasing your costs.
So Teijin makes Tvaron, which is one of the commercial brands of PPTA fibers. It's very similar to Kevlar. They used for high-strength applications like ballistic protections. And because the method for making Tvaron is so similar to the method we use for making nanotube fibers, Teijin got interested into working with us. They are real artists in the art of fiber spinning, and they have been able to move the technology so much faster than we could have done just by ourselves.
Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. Dozens of videos have been made on graphene, and most of them cover the same key talking points. My goal in this video is to provide fresh information along with a better industrial and commercial perspective. I'll cover the basic chemistry of graphene, production methods, the ISO standard definitions for the different types of graphene, and when we can expect to start seeing graphene in products. Let's get right into it. Most of you already know what graphene is. It's a two-dimensional molecule that has the highest strength of any material and remarkably high conductivity. But why does it have these characteristics? To understand this, we'll need to take a closer look at carbon. Bear in mind, the explanation I'm about to provide is a simplified version of much more complex phenomena. Carbon forms a sigma-type covalent bond with other carbon atoms. A sigma-type covalent bond is one where atoms share electrons equally between each other, such as H2, which is hydrogen bonded with hydrogen, also known as hydrogen gas. A sigma-type covalent bond is the strongest type of chemical bond because the shared electron acts like a rope, holding the two atoms together. However, we don't typically think of hydrogen as strong. This is because a pair of hydrogen atoms is just too small to handle. To take advantage of the strength of a covalent bond or test it, we need a large enough chain of these bonds to make a material we can physically handle. This is where carbon has a trick up its sleeve. This is an illustration of a graphene ring. The carbon atoms are represented by the spheres, and the covalent electron bonds are represented by the tubes. Each carbon sphere has 4 electrons that it's willing to share with other atoms to form covalent bonds. 3 of these electrons can be shared with other carbon atoms. As you can see, each carbon atom is bonded to 3 other carbon atoms. The chains of covalent bonds form the familiar chicken wire structure of graphene. With an even larger sheet, those covalent bonds can actually be useful in products to make them stronger. If you're wondering why graphene forms into rings with 6 atoms, it's because 6-atom rings are the most thermodynamically stable for carbon. It's possible to have more or less atoms in the ring, but that's not desirable because it's less uniform and less stable. What about conductivity? I mentioned a moment ago that carbon has 4 electrons to share, but it only shares 3 with the other carbon atoms to form graphene. What happened to the last lonely electron number 4? It bounces around the graphene structure. In fact, every single carbon atom has a spare electron that it's happy to share around. Electricity is a flow of electrons. If the atoms within a material are happy to share electrons, they're just as happy to let new electrons in and let other ones go. This is exactly what graphene does, and it's what makes graphene 1,000 times more conductive than copper. Graphene has many other properties, but its structure and conductivity are the main properties I'll focus on in this video and future videos. There are 2 general methods to manufacture graphene: bottom up and top down. I'll provide examples of each of these methods. Before we begin, one note on quality. When I use the word quality, I'm referring to materials that have higher conductivity and strength. Let's start with bottom-up graphene. With bottom-up graphene production, the graphene is assembled atom by atom to form a single sheet and is often referred to as a film. This is what most people are thinking of when they hear the word graphene. The ISO definition of this is one-layer graphene. We'll get more into ISO definitions in a moment. As you would expect, the bottom-up, atom-by-atom method is slow and prone to error. It takes trillions of atoms to even form a small piece of material that's maybe a few millimeters square. For one-layer graphene films to be useful, they have to be pristine. That is, without holes in the graphene film. This is why it'll likely be a decade before we see one-layer graphene in mass production. Let's take a look at where this technology is right now. Graphene is a 2-dimensional crystal, and like other crystals, the best way to build it is to grow it. In other words, it's too difficult to physically build a crystal atom by atom. Instead, you provide the right environment and materials, and the crystal will build itself, atom by atom. The way this is done with graphene is to heat a copper plate in a chamber filled with gas, such as methane. The methane gives up its carbon atoms to the copper plate, and in the process, the graphene self-assembles on the copper plate. This is called chemical vapor deposition, or CVD, and that's the easy part. Now that you have a copper plate with a layer of graphene, how do you remove the graphene that's stuck to the copper plate so you can use the graphene? In short, this can't easily be done without ruining the graphene. However, researchers from MIT published a paper a few weeks ago that claims to have solved the sticky graphene problem. They first grow a layer of parylene on the copper plate using CVD. Parylene is a polymer coating used in the electronics industry, so it's not anything exotic. After the parylene layer is grown, then the graphene layer is grown on top of it. The parylene layer is like putting parchment paper on a baking sheet when making cookies. It's a lot easier to lift cookies off the parchment paper than a bare metal baking sheet. The same is true with removing graphene from the parylene instead of bare copper. The researchers claim that the graphene can be lifted off the parylene easily and without damage. Great. So tomorrow we'll see graphene products on shelves. Not so fast. It takes years to perfect production processes and get them to the point where they can drive the cost of a material low enough so that it can be put in any product. Even when the cost of the material is low, it takes time to convince industries to switch to that new material. it'll be at least a decade before we see one-layer graphene films disrupting industries. This takes us to top-down graphene production methods. Instead of building the graphene atom by atom in pristine sheets, it's made from a nearly unlimited supply of graphene that Mother Nature's provided. Graphite. Graphite is formed when rock containing high amounts of carbon, such as coal, is exposed to high pressures and temperatures. This causes the high graphene rock to stratify and form into perfect graphene sheets, millions of layers thick. If the pressure increases further, diamonds form. Top-down graphene production is the process of splitting graphite apart, layer by layer, to release the individual graphene sheets. Another word for this is exfoliation, because it's similar to removing a layer of skin. To understand how to create quality graphene through exfoliation, it's best to first look at a primitive method of exfoliation. The graphene sheets in graphite are stuck together by a force called van der Waals force. Van der Waals force, in the simplest terms, is a type of static electricity that happens at the molecular level. It's a weak bond that can be broken with little force. One way to disrupt that bond is with high concentrations of acid in a process called chemical exfoliation. The acid disrupts the bonds by turning the graphite into graphite oxide. The graphite oxide is much easier to mechanically exfoliate because it creates groups of oxygen atoms attached to the edges of the graphene that makes up the graphite. The best way to think of these oxygen groups is like a bookmark sticking out of a book. It's much easier to open the book with the bookmark. With these bookmarks in place, it's easier to mechanically break up the graphite oxide with methods as simple as stirring. The result of breaking up that graphite oxide is graphene oxide. Graphene oxide is a lower quality material and doesn't exhibit all the excellent qualities of pure graphene. There are several ways to repair graphene oxide, but they range from toxic to energy-intensive to time-consuming. None of them are ideal. Regardless, it can be done, and the result of the repair work is reduced graphene oxide, or RGO. RGO still has some imperfections, but it's nearly graphene and useful in industrial applications. What's the difference between all these forms of graphene? Graphene oxide is relatively strong, RGO is stronger, and graphene is the strongest. With regards to conductivity, graphene oxide is relatively non-conductive, RGO is conductive, and graphene is the most conductive. However, graphene oxide and RGO have some qualities that graphene doesn't. For example, they're both soluble in water, whereas graphene isn't. In other words, graphene is considered the highest quality material, RGO is second, and graphene oxide is in third. With that in mind, let's move on to a more advanced top-down process. This video is from a company called Tolga Resources and shows a top-down method of graphene production called electrochemical exfoliation. As the name implies, it involves chemicals and electricity. What's happening here is that the electric current from the electrodes is driving ions from the solution into the structure of the graphite. This is possible because the graphite ore that Tolga has access to is conductive straight out of the ground. When the ions from the solution are driven between the graphene sheets and the graphite, they react in the solution to form gas bubbles. The gas bubbles split the graphite layer by layer, causing the graphene to exfoliate. Notice that this kind of looks like ink or powder. I'll explain what this is when we get to ISO standards. You might assume electrochemical exfoliation requires toxic or exotic chemicals. However, the research I've found indicates the solution can be made with chemicals as simple as ammonium, which is a cheap material that's often used as a fertilizer. This doesn't rule out toxic side reactions, but we can't know for sure without knowing more about Tolga's process or formula. In general, the process isn't without its challenges. For example, the graphite can disintegrate before it's fully exfoliated into graphene. The way this happens is that as soon as a piece of graphite is disconnected from the graphite that's connected to the electrode, the ions stop being driven between the sheets of graphene by the electricity. When this happens, the result is tiny pieces of graphite rather than graphene. The research paper shown here proposes a way to stop these pieces of graphite flaking off before they're finished converting to graphene. The researchers enclose the graphite in a mesh that holds the graphite in contact with the electrode. The result is a graphene material that's better quality than graphene oxide, which, as you remember, was the relatively non-conductive and weakest graphene material from the chemical exfoliation method. However, the quality isn't as high as the reduced graphene oxide, which was the repaired form of the graphene oxide. However, with some minimal processing, the graphene produced from the electrochemical exfoliation method was comparable to the reduced graphene oxide in terms of conductivity. Tolga claims to have trade secret processes that are likely better than what were outlined in this research paper. Regardless, it seems like the challenges with electrochemical exfoliation can be addressed. There are other ways of mass-producing top-down graphene that are just as promising as what we've seen from Tolga. The privately held company BZ Graphene uses a purely mechanical process called liquid phase exfoliation. Liquid phase exfoliation is a type of mechanical exfoliation. Mechanical exfoliation includes methods such as using ultrasound on graphite suspended in a liquid to exfoliate the graphene from the graphite. I had a chat with Milos Dunko, the CEO of BZ, and he pointed me to the ISO standards for graphene. We'll need to understand these before we go any further. In 2017, the National Physical Laboratory in the UK published ISO standard definitions for graphene. I haven't seen any other graphene videos cover these definitions, which are essential to any discussion on graphene. These are the key definitions. A single layer of graphene is called one-layer graphene. A double layer of graphene is called two-layer graphene. 3 to 10 layers of graphene is called few-layer graphene, and 11 to 3,000 layers of graphene is called nanoplatelets. Not graphene nanoplatelets, simply nanoplatelets. This is because that many layers of graphene are technically no longer graphene. Larger than 3,000 layers is graphite. The BZ collateral claims that 90% of what companies claim is graphene is actually nanoplatelets rather than graphene flake. What do I mean by flake? In this video, there was what looked like an ink or powder precipitating off the piece of graphite that Tolga was running electricity through. That's what single, two, few-layer graphene and nanoplatelets exfoliated from the graphene look like to the naked eye. At the microscopic level, that inky material looks like flakes, and so it's referred to as flakes. All the top-down methods covered in this video produce graphene and nanoplatelet flake in different ratios and qualities. For the rest of this video, I'll refer to all those different forms, including nanoplatelets, as simply graphene flake. Graphene flake is used as an additive. In other words, it's added to other materials to give those materials some of the qualities of graphene, like conductivity or strength. It only takes a fraction of a % of graphene flake to begin to alter the properties of the material that it's added to. In other words, graphene flake will be both low cost and not much will be required to get the benefits. One last note on BZ's process now that we understand the graphene flake. BZ refers to their liquid phase exfoliation machine as a reactor. They claim their reactor produces high-quality flake and that they can adjust the reactor to produce one, two, or few-layer graphene flake. I'll be watching both Tolga and BZ closely in the coming years. Time for a recap, because that was a lot of definitions. There are two broad graphene materials. The first is graphene films, which are pristine one-layer graphene, produced atom by atom in a bottom-up process and are at least 10 years away from mass production. The second broad material was graphene flakes. These were one, two, few-layer, and nanoplatelets. Graphene flake is produced with a top-down method, and some producers are already ramping production. Primitive methods of producing flakes create damaged material called graphene oxide. Graphene oxide can be repaired somewhat, and after the repair process, graphene oxide is then called reduced graphene oxide, or RGO. There's a third form of graphene, which is of course graphite, but that'll be covered in upcoming videos on anode materials. This pie chart from Tolga Resources is a forecast of how much market share each form of graphene flake is expected to have in 2024 and provides an insight into what types of products the flakes will go into. The chart is missing two-layer graphene. However, it still gives a good indication of the commercial market. Each form of graphene has uses, even nanoplatelets which aren't technically graphene. If we eyeball the chart, in 2024 it looks like only 15% of the graphene market will be for single-layer graphene. The chart doesn't specify whether that's single-layer flake or large single-layer films. Regardless, the single-layer materials will be used in products like solar panels and flexible electronics. Another 15% will be used for commercial products such as paints, coatings, and circuit boards. The remaining 70% will be used for industrial products such as lubricants, composites, and energy storage. The chart doesn't specify, but my assumption would be that this pie chart is in terms of revenue. I expect that thousands of tons of lower margin flake will cover commercial and industrial uses, whereas the premium single-layer flakes or films will go into higher-end products with larger margins. If the pie chart were split by weight rather than revenue, the single-layer and few-layer flake would take up less of the pie chart. Most of the hype around graphene is around cutting-edge personal technology. I'm as excited about those use cases as anyone, but I think graphene will change the world in more subtle and important ways. This slide from BZ Graphene illustrates just what a turning point graphene is. Every era of human technological development has been marked by a material that allowed us to bring the things we imagine into reality. The era we're entering now is the graphene age. Graphite is cheap and plentiful, and when processed into graphene flake, it has few rivals in terms of conductivity. Nearly everything will have graphene in it, just as nearly everything now contains plastic, metal, fabric, concrete, and glass. All these materials can be improved with a few weight % of graphene flake, and I expect all of them will. We'll be able to strip more plastic out of our packaging, remove toxic metals from industrial paints and coatings, make our buildings into new shapes and with less material, make electric flight part of our day-to-day lives, and make life in space and on other planets a reality. This will be compounded by multiple other revolutions happening at the same time in genetics, aerospace, renewable energy, nanotechnology, brain-machine interfaces, artificial intelligence, and batteries. So where are we with graphene now, and when can we expect this future? This slide from Tolga Resources shows where graphene is currently at. Right now, bulk production of graphene flake is being established, and new materials are being tested. In the next few years, the first volume leaders in the industry will be established. From 2022, some manufacturers will start to become familiar with graphene-based materials. Graphene will quietly make its way into materials like product packaging, specialized concrete, and industrial paints. It'll enter the market more loudly in products like high-end sports equipment and maybe cell phone batteries. We'll come back to batteries in a moment. After 2025, the real graphene boom will begin. Graphene will filter its way into products from luxury down to budget. From 2030, graphene will hit its stride with mass adoption. Companies will be putting graphene flake into everything that supply and budget will allow, and large single-layer graphene films will begin to hit the mainstream. With graphene and all the other technological advancements going on, we'll be getting the first inklings of the sci-fi promised land in our lived physical world. A moment ago I mentioned batteries, and I'll close on that topic. I'll provide an executive summary now for those who've been asking about graphene and batteries. In the future, I can make an entire video on graphene and batteries. There's many ways that it can be used to improve their performance. The most likely way for graphene to be added to batteries is by adding graphene to the anode. The type of graphene used for this would be the few-layer graphene or nanoplatelets we discussed above. Adding graphene to the anode improves charge rates and cycle life but doesn't improve energy density. Due to the further processing in small supply, graphene is and will continue to be more expensive than graphite. So not only is this graphene flake more expensive than regular graphite anode, it doesn't reduce the amount of material needed to make the battery. Expensive batteries work for small personal electronics like chargers and mobile phones. However, vehicles require thousands of cells and cost is more of an issue. Tesla and other manufacturers are primarily focused on making the batteries cheaper, which means getting rid of expensive materials and using materials that are more energy dense so less material can be used. Graphene doesn't improve energy density or reduce cost. so I'm not expecting to see it in automotive batteries within the next few years. Now that we have a good understanding of graphene, we'll move on to anode materials in the next two videos. Novonics, by popular demand, will be covered in the next video, and the video following that will be on Tolga resources. Graphite anodes are far more interesting and far more promising than they get credit for, and I'm looking forward to sharing what I've learned. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video, or snag something off the merch shelf below. I'm also active on Twitter and Reddit. You can find the details of those in the description, and I look forward to hearing from you. A special thanks to Dervin Brown, PM Nordquist, and Neil Pitts for your generous support of the channel and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.